Okay, this next little unit is kind of like a little mini unit, and it's for honors kids only. On level kids, you guys do not have to know anything for this next unit. But this is kind of an extension of my covalent bonding. We are going to talk about organic structures. So organic chemistry is the study of the structure, the properties, and the reactions that carbon-containing compounds can do. And these carbon-containing compounds, or these organic compounds, are the basis for all of life, okay? So you guys in biology learned about the cell, and the cell is made up of a bunch of stuff that has carbon, okay? So this will be a wonderful tie-in to biology, which you know I love. So I thought we would do a little lesson on an introduction to what organic chemistry is. There are no slides to go over in this unit. We will be working on our notes handout because a lot of it is practicing drawing structures. And no, this unit is not all OChem. That is for you to enjoy when you get to college. But I thought we would kind of scratch the surface and be able to kind of identify what some of these organic structures look like and be able to maybe draw our own and name some, which is super fun. Okay, so let's get into it. What I'm going to be using today is I'm going to be using obviously a pencil because we're going to write things. And I'm also going to be using a highlighter probably quite a lot. Maybe not for this first lesson, but this highlighter is going to do some work for us when we get into talking about alkanes, alkenes, and alkynes, which I'm super excited about. Okay, so let's start. So we said organic chemistry is the study of carbon compounds, you guys. Let's talk about carbon then. It says carbon has 4 valence electrons. We know that because y'all, look, he is in group 14. He's got 4 valence electrons, okay? So I'm going to draw the electron dot structure for carbon with his 4 valence electrons. There he is. He looks real good right there, doesn't he? Okay, so the next thing we're going to do is it says each atom of carbon can form 4 covalent bonds. Draw the Lewis dot structure for CH4. Now, previous to today, we would be calling that carbon tetrahydride, which is a correct name for this molecule. But we're going to get to learn how to name these organic compounds in different ways. So this is technically methane. Do not be afraid. We will talk about how to name this here in a second, but we're going to draw the Lewis dot structure for methane. So we know that we first count up total valence electrons that are available to be shared between all of these atoms. We know carbon has 4, and each one of my hydrogens, which I have 4 of them, have 1. So my total number of valence electrons to distribute throughout this molecule is going to be 8. I'll zoom in a little bit here for our structure of our Lewis dot structure for methane. So I'm going to put my central atom in the center, who is carbon, and my outer atoms on the outside, which are my 4 hydrogens. Connect everybody up to the central atom with a bond. So 1, 2, 3, 4, 5, 6, 7, 8 valence electrons were used in the forming of those 4 bonds, which means I have used up all of the possible valence electrons from all of those atoms in this molecule. And it looks like hydrogen is satisfied with 2 electrons on each hydrogen, and totally I got 4 bonds, which we know if each bond is 2 electrons shared, then that carbon now has a full valence shell of 8. Okay, so the cool thing about this organic chemistry stuff, since it's focusing on these carbon atoms, I am dealing with covalent bonding. So that is why I've placed this mini unit right after our lessons on covalent bonding, because this is all dealing with these connecting Lewis dot structures as well. Okay, so carbon is the basis of all of these organic compounds, which is really exciting. Okay, so let's talk about organic compounds. Oh my goodness. Organic chemistry involves the chemistry of compounds containing multiple carbon atoms. Because of carbon's unique ability to bond with itself and with other atoms in a variety of different ways, there are millions of possible organic molecules. So here's the beauty of carbon having 4 valence electrons. Y'all, not very many atoms on the periodic table do a lot of covalent bonding when they have 4 valence electrons. I'm looking up here and on my staircase and I'm like, these are your 2 nonmetals here, you guys. Carbon being able to form having 4 valence electrons means he is able to form 4 bonds. That is a lot. Most other elements on the periodic table only have the ability to form 1 bond or 2 bonds or even 3 bonds, but carbon's like, yo, I can form 4 bonds. With this, the possibilities are kind of endless on the type of compounds that I can create. So here I have some examples here of some interesting looking guys. Y'all, look at this guy. Oh my gosh. And we're going to learn what all of the little lines mean here in a second. But I can see here some carbons and some hydrogens stuck together. And this is a wackadoo structure. Zoom in a little bit more. Oh my goodness, look at that guy. That's a lot going on there. Got some more stuff. So the possibilities are endless, y'all, on these organic compounds because carbon can bond a lot. Okay? So it says not only are organic compounds a vital component in living things, they can also contribute to a wide variety of materials that we use in our modern lifestyle. Hydrocarbons are the simplest of the organic compounds, and they're made up of carbon atoms and hydrogen atoms. Hydrocarbons are carbon and hydrogen. We love that. Organic compounds can also contain some of my halogens, right? I got some nitrogen in some of them. I got some oxygen in some of them, phosphorus, sulfur. A lot of these nonmetals, meaning stuff that can also make covalent bonds with carbon. Organic compounds have several unique properties. They have relatively low melting points and boiling points. Well, they are covalent structures, right? We've talked about that covalent structures or molecules, it doesn't take a lot of energy for them to melt from a solid to a liquid, and it doesn't take them a lot of energy to boil from a liquid to a gas. And that is because of the weak IMFs that are between the molecules, allowing the different molecules to spread out away from each other. They also tend to be insoluble in water, and they're really bad conductors of electricity because when I drop an organic compound into water, not only may it not be soluble, it's also not going to break apart into ions. We know the covalent bonds themselves holding these molecules together are really strong, and so they cannot break apart and create those mobile ions which are needed to conduct electricity. All right, I'm super excited. Okay, so we are going to practice drawing structural formulas for some of these organic compounds containing carbons. It says, recall that carbon has 4 valence electrons, so each carbon atom can form 4 covalent bonds. Here is a sample problem for us. It says, using structural formulas to represent organic compounds. So as we saw up here, there's lots of different ways that I can represent my organic structures. Some of them you got a little bit more letters of the alphabet. Some of them you do not, okay? These are different ways I can represent organic compounds, okay? It says butane is a fuel used in lighters. It has the formula C4H10, and it has 4 carbon atoms attached to each other in a chain with only single bonds. Draw a structural formula for butane. So what we're going to keep in mind here is we're going to draw some different types of structural formulas here for butane. And I'm going to write this a little bit bigger off to the side. So the formula for butane is C4H10. Clearly, I can see that they told me in here that is at 4 carbons. Yes, I see a 4 subscript underneath the C, so that means he has 4 carbons. And I've got 10 hydrogens. Well, yeah, y'all, this is totally a hydrocarbon. A hydrocarbon is a compound made up of carbon atoms and hydrogen atoms. Yep, it looks like that's what I've got here. They also told me that the atoms, the carbon atoms, are attached to each other in a single chain with single bonds connecting them. So that's something to keep in mind as we're moving on forward. And I love this little thing because it kind of walks you through it. Things to think about. So what are we thinking about here? It says the 4 carbon atoms are bonded to each other in a chain. So draw 4 carbon atoms attached to one another in a line. So here we go. Are we ready? So we are going to draw 4 C's attached to each other in a line. Sounds good to me. Each one of those lines you have drawn is a bond. So that is 2 shared electrons between each one of these carbon atoms. Great, so we just tackled the first thing on what to think about. Then it says each carbon atom can form 4 covalent bonds. The first carbon atom, he's got 1 bond already connecting him to the other carbon atom, right? So he can form 3 more bonds potentially, and he will. But those 3 more bonds that he's going to form are going to be connected to hydrogens. So I've got 1 hydrogen, I've got 2 hydrogens, I've got 3 hydrogens. Yes? So once again, I'm seeing carbon with 4 bonds. 1 bond connecting to the other carbons in the chain, and that leaves 3 available bonds to connect to hydrogens. Okay, it says the next 2 carbon atoms have, well, they've got 2 other carbons attached to them, right? So they've already got 2 bonds with 4 valence electrons. So then they have the potential to make 2 more bonds, and only 2 more bonds, and they're going to make those bonds with some more hydrogens. So this guy right here, he gets 2 more bonds. Yay, you get a bond to hydrogens. Same thing with this guy. He's already got 2 bonds on him, so his 2 other bonds will be to some hydrogens. Okay? The last carbon atom is already bonded to 1 carbon atom in the chain, so therefore he can form 3 more bonds. And you guessed it, he's going to form those 3 more bonds to hydrogens. Y'all, we have just drawn butane. Let's check this out. Does it have 4 carbons? It sure does. Well, does it have 10 hydrogens? Let's check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Amazing. So this is a hydrocarbon. You get a chain of carbon atoms, and then you're going to fill up the carbons with hydrogens to where each carbon will have 4 bonds, which is super exciting. Okay. Now, this is a full structural formula where I'm showing every single bond and every single atom or letter of the alphabet required here in that structure, okay? But I can condense it down here into a structural formula by just being like, okay, this entire guy right here is carbon with 3 hydrogens. And this entire guy right here is carbon with 2 hydrogens. And this entire guy is carbon with 2 hydrogens. And this entire guy is carbon with 3 hydrogens. So I can actually write this as a structural formula, which is a little bit less in detail than the full structural formula, to where I would just be like, yep, that first part, you guys, is a CH3. And when you see a CH3, it is understood in your brain that, oh yeah, okay, that looks like that. And then my next guy, he is a CH2. And then my next guy is a CH2. And then my last guy in the chain is a CH3. So what I'm looking at here is I can very easily and visually see the 4 carbons in this 4 carbon containing compound, this butane compound. And it kind of eliminates just the chaos of all those hydrogens flying at you, because I'm going to let you know all of these organic structures, we got hydrogen just kind of slamming on in there, taking up space to keep these atoms satisfied. So, and it's also easy to see that the ends of these chains have the ability to attach to 3 hydrogens because they only make 1 bond to the other carbons. Whereas my middle guys in here who are trapped by 2 other carbons, they can only fit 2 hydrogens in there to complete their octets. So that's a lot more visually satisfying, okay? I can even condense this structural formula even more by writing the number of hydrogen atoms bonded to each carbon, but now I can get rid of the dash. Watch how this looks. I can go CH3, CH2, CH2, CH3. So that is a super condensed structural formula. I have written it in this way to show you what each carbon has on it. So this totally still, as read, has 4 carbons and 10 hydrogens, but it gives a little bit more detail than this does, showing how all those hydrogens are arranged on the compound into which carbon they are on. Okay, so this is a condensed structural formula. Now this one's my even most favorite one. This one is wackadoo, but you will see this a lot, especially in giant organic compounds. This is called a skeleton formula. And a skeleton formula is a little bit wackadoo. I just get rid of all of the letters of the alphabet and I draw like jiggity jag lines. Let me tell you what I'm talking about. So this butane has 4 carbons. So a butane skeleton formula is going to look like this. There it is. You were like, what did she just draw here? Okay, The way a skeleton formula looks, or what is understood by it, is every single time you see a point or an end of a line or one of these points, those are actually carbons. So I would be able to see this. I'm like, yep, I got 1, 2, 3, 4 carbons. Boom. And you were like, well, where did the hydrogens go? Here's the beauty of knowing that carbon can make 4 bonds. If I see a carbon over here on the end, we know he's on the end. If he's on the end, we know he's got to have 3 hydrogens bonded to him. You do not need to tell me that. If we got a carbon here on a point within the middle of the molecule, we know if he's bonded to 2 other things already, being those carbons, he's got to have 2 hydrogens on him. Same thing. This guy's got to have 2 hydrogens. And this guy on the end, we know he's got to have 3 hydrogens. So just by knowing that carbon's got to make 4 bonds, whatever things he is connected to in the carbon chain, we can fill in our brains knowing how many hydrogens must be there. So in terms of what we will be most commonly writing and drawing in my class, is we are most commonly, when it comes to our practice, which there's not a ton of practice today. Today's mostly like an intro into organic structures. But we tend to be doing these structural formulas, showing what each carbon in my chain has on it. And the separation of dashes really does help you guys figure out and allows you to maybe create some branches off of these individual carbons. This condensed structural formula, even though for this specific example you're like, it looks exactly the same except for the dashes, the condensed structural formula will never have any jutting off lines and connecting things above or below it. It'll always be written in a straight line as if you are reading a book, and we'll practice doing all that stuff later. But this guy, this structural formula, is what we will be hanging out with for this unit. Okay, so now let's flip to the back. This is very exciting. Ooh, the guinea pigs are excited, so you know it's going to be good. Okay, this is a little bit of an intro. Our next lesson is actually going to be on naming branched alkanes, which is where things get a little bit more challenging. It's not challenging, but a little bit more in depth. But I thought we could, since we're on the topic of hydrocarbons, we could be like, okay, let's focus on what the simplest kind of hydrocarbon is. And the simplest kind of hydrocarbon is what is called an alkane. And I'm going to get my highlighter out, and I'm actually going to highlight the end of that word, alkanes, noticing that ane ending, okay? And I mentioned these are the simplest of the hydrocarbons. That's because they're hydrocarbons that only contain single bonds, okay? Well, if I flip back at my little butane, yep, each one of these lines is a single bond. That looks good to me. It looks like we got an alkane so far. It also says they are saturated. What now? Saturated. That just means that every single carbon atom is going to be bonded to 4 other atoms. And guess what? When I'm bonded to 4 other atoms, that is going to require me having a ton of hydrogens involved. Okay, so single bonds, and they are saturated, right? The ending of all alkanes, meaning if I'm to name a specific alkane, will end in ane. I keep flipping back and forth, but here we go. We wrote this for butane, right? It told me butane, ane ending. So it is an alkane. But y'all are like, well, where did I get the but from? We're going to get here on that. But the structure or the molecular formula of any alkane is going to be this. Let's zoom in on this real quick. Yes? That little teeny tiny n just means you can put any number there. In our butane example, we had a 4 subscript, right? But then you can actually figure out how many hydrogens are required to get that carbon chain fully saturated. I know over here, I'm not going to flip over anymore. I'm just going to write my butane example. We wrote C4H10. That was what we worked on the other side of this page, right? Now, you could either draw the structural formula like we did, knowing that carbon has to make 4 bonds and see that there will be 10 required in there, or you can just look at this and say, hey, whatever the number of carbons is, multiply it by 2 and then add 2. And that will be the number of hydrogens you have, okay? So 4 times 2 gives you 8. And if I add 2 more to that, that's required to get you to the 10 hydrogens. So that's a little kind of unique way to figure out how many hydrogens you have, depending on, what was I saying? depending on the number of carbons. Okay, cool. Now let's bounce out here. You're like, okay, butane. What is she going on here? I have some prefixes in organic chemistry that if you see a subscript underneath a carbon, it will tell you how many carbons you have. There will also be a specific prefix required to name that alkane molecule. So what I've got here is if I have 1 carbon, my prefix is meth. If I have 2 carbons, my prefix is eth. If I have 3 carbons, my prefix is prop. If I have 4 carbons, my prefix is bute. That's where the butane came from. So this is my butane, okay? And then I get to pent and hex and hept and oct and non and det. Okay, these you guys know. These are the prefixes that we use for any covalent compound, not only organic structures, but organic chemistry, I feel like, has this overarching theme that it likes to make itself difficult for no reason. And specifically for these organic or these carbon chain containing compounds, we use these prefixes for the first 4, okay? And the way that I remember this meth, eth, prop, bute, is this is gonna make, this makes no sense, but I luckily am too old to feel embarrassed anymore by this, but the way that I think about this is I think me eat peanut butter for methane, ethane, propane, and butane, because the MEPP. So we will write that. And I have remembered this for a long, I would not say how many years that is, but it has been a long time. So me eat peanut butter. That gets me through the first 4 prefixes, and then after I cruise through those first 4, pent, hexa, hepta, all of those are just the same as what we're used to. Very exciting. Okay, so me eat peanut butter. All right, so now we got some practice. You know, I like some practice. It says, what would be the molecular formula, which once again, the molecular formula is just how many carbons you have and how many hydrogens you have. What would be the molecular formula for a straight chain alkane that had the following number of carbon atoms? Okay, 6 carbon atoms. Well, let's start in here hot with our simplest thing. We got 6 carbon atoms. Yay for us. Well, I need to make this an alkane. That's a chain of 6 together. How many hydrogens are you going to need to fill up all the outside? Well, I'm going to take that number, 6 times 2, to get 12, and then I add 2 to that. So that would be H14. Nice. So if I were to draw this out, it would be 6 carbon chain, and there would be 14 hydrogens needed to completely saturate all of those carbons, or saturation means giving it a 4 carbon bonds, right? Or 4 bonds to each carbon atom. All right. Next guy, we got 12 carbons. Yay. So C12, right? And let's figure out how many hydrogens we need. 12 times 2 is 24. 24 plus 2 is 26. Okay. Guys, we can even name this guy right here. Y'all want to name him right now? So he is an alkane, right? Because I have a complete saturation, meaning the number of hydrogens is double that plus 2. And so I will find my prefix for 6, and I see it is a hex. So we will call this a hexane. We love that for us. No, I do not have a prefix for you for 12, so we will not worry about that. You can worry about that when y'all get to college, or not if you do not wish to take organic chemistry in college, which you're missing out if you're not going to want to take it, because it is a good time. All right, here's something also wild and crazy. We got 29 carbons coming in hot. 29 carbons. Whew, that's going to be a lot of hydrogens. Let's think. I would have grabbed my calculator if I have it handy, and I do not, but let's see if we can do it in our head. 29 times 2, that is 58, right? Plus 2 is, I think, 60. I'm really hoping that that is correct. But what we have done, we multiplied that by 2 and we added 2 to that. Amazing. All right, next up, we've got 32 carbon atoms. Oh, why am I making this more challenging on myself? These numbers keep getting bigger. Not a big deal. So the number of hydrogens is 32 times 2, which is 64. 64 plus 2 is 66. Now you're like, why is she just giving us these like giant numbers for carbon? That is like so dumb. No, it is not dumb, because we've got these giant things in our bodies specifically that have these really long carbon chains. Specifically, a flashback to biology, we know that the cell membrane, or the outside of each one of our cells, is made up of a phospholipid bilayer. when I've got really long saturated carbon chains, meaning carbons that I've got all the hydrogens, but like 29 of them in a row or whatever it was on the other page in a row, that's what creates part of that phospholipid bilayer, these really, really long hydrocarbon chains, which when they're saturated like this are not soluble in water, which is why the cell is able to have a differentiation between the inside of the cell and the outside. It does not allow very easily the passage of water through it. Wow, I'm not a biology teacher. Why did I get into that? Well, I was excited, that's why. But yeah, like that is totally available for, we get long chains like that too. I love that for us. Okay, now we're getting into the more fun stuff. I'm getting really excited. Okay, so complete the chart. We love a chart to complete. All right, I have given you the molecular formula, which shows you the number of carbons and the number of hydrogens in these alkanes. I want you to name them. And then I want you to draw the full structural formula. Once again, let's review what a full structural formula is. It's like, oh my gosh, showing all the hydrogens and the bonds to the hydrogens. And then I want you to do a condensed formula. And so the condensed formula is eliminating all of those bonds, just showing what is on each one of those carbon atoms. Okay, here we go. We're excited. All right, let's name this guy first. So I see a 2 here. That 2 is important because the prefix of 2, eat is eth. So I have ethane. This is ethane. How exciting for us. So that eth means my 2. All right, so my full structural formula, the way we do this, and it told you on the first side of this page what you do to eventually get to your full structural formula. You first chain up all of those carbon atoms together. Ready? There are only 2 of them, so it's not going to be super exciting. Boom, boom. And then I'm going to tackle each carbon one at a time and give it the more bonds until it gets 4, right? So he needs 3 more bonds, right? And each bond that I'm drawing is going to be connected to a what? A hydrogen. And then my guy at the end, my other carbon, will also need 3 hydrogens. So that's my full structural formula, the whole picture. We love this for us. Now I'm going to condense that down to where I'm just going to be like, how many hydrogens on you? And how many hydrogens on you? We're just going to write that, which means my first carbon had 3 hydrogens, CH3. The next carbon, which is also my last carbon, also has 3 carbons. So this is a condensed formula for a simple hydrocarbon alkane ethane. All right, this is getting fun. Here we go. I've given you the name. Propane, propane, propane. Me eat peanut. Propane means 3 up here, right? So propane, propane, we know that is 3. So I've got C3. You're like, uh-oh. Well, I can tell from the ending ane. Okay, that means that I will figure out how many hydrogens I have by multiplying the number of carbons by 2 and then adding 2 to that. So I have 3 times 2, which is 6, plus 2, which is 8. So propane is C3H8. And some of y'all are thinking like propane, like gasoline? Yeah. So these organic structures not only are good for our bodies and all life, but I'm finding some other uses for them just, to help us in the world as well, which is exciting. Okay, chain all 3 of them up. 1, 2, 3. Saturate each carbon by making sure he has 4 bonds. 1, 2, 3. This one needs 2 bonds, right? Because he's already bonded to 2 other carbons, so he can only make 2 bonds to a hydrogen. Yes, very exciting. So that's my full structural formula for propane. Condense it down and show me what each carbon has on it. We have a CH3. The second carbon has CH, only 2. And the third and final carbon has CH3. So there's propane, yes. All right. Next up, pentane, pentane, pentane. This is a prefix that is old news for us. We know pent means 5. So we have C5H. Okay, for these alkanes, we know we multiply times 2 plus 2. 5 times 2 is 10, plus 2 is 12. Okay. All right, so we're going to draw 5 carbons all chained up in a row. So we got 1, 2, 3, 4. Whoopsie, I went too far. That is okay. We can make space for it. Each carbon, make sure he gets 4 bonds by saturating him with hydrogens. This is the point to where y'all are like, oh, drawing these full structural formulas are just so time consuming with all of the letters of H that I have to draw in there, which I agree, which is why I'm not forcing y'all to draw them that often, but I think it does do a great job, especially when we're getting an intro on what these hydrocarbons look like, kind of checking and noticing, oh yeah, yep, if I counted up all those hydrogens, that would give me 12. It also really shows that carbons have 4 bonds, okay? That's how I'm getting actually that number of hydrogens. So there is a purpose in that for right now, I think. Condense it down. Tell me what each one of those 5 carbons has on it. First carbon, CH3. Then we got CH2. Then we got another CH2. Then we got another CH2. And then we got another at the end, CH3. Once again, looking at the ends of my chains, can have 3 potential hydrogens. And my middle guys here, they can only have 2. All right. Last one. We got 7, C7H16. And guys, I didn't talk about this, but we can check based on the number of hydrogens. We can check if it's going to be an alkane or not, because we're going to want to expect that number of hydrogens to be 2 times the number of carbons plus 2. Let's see if this makes sense. Okay, so 7 times 2 is 14 plus 2 is yes. Okay, so this is truly an alkane. So when it comes to naming it, I know 7 is going to be hep. But now I feel confident putting down an ane ending, letting me know that this is a completely saturated alkane. Y'all are like, wait a minute, she's telling me that this may not be ane at the end. Yeah, we have potentials of that being a different ending depending on what else is. I'm not going to scare you off that now, but that's a good way to check, making sure that my molecular formula rules for naming these alkanes supports the name that I'm actually showing. Okay, so now let's do the full structural formula. Oh, I'm such a mean person. 7 carbons. Here we go. 7 carbons in a row. I feel like I'm taking up more space than I should. Yep. Oh my gosh, I will be taking up a lot more space. I did not plan that out, did I? That's okay. We can roll with this, right? So I got 7 carbons in a row. We know that the ends of this alkane will have 3 hydrogens, and each one of the middle carbons we'll get 2 more. I'm already getting tired. My hand. Oh my goodness. Okay. Yes. Woo, that was a lot. But yes, if I were to count all those hydrogens, there will be 16. My hand feels like I had to draw 16 H's. All right. So now we're going to draw the condensed formula showing what each one of those 7 carbons have. I'm actually going to write it down here because I do not think I can get that much in here. So my first carbon is a CH3. Then I got quite a few CH2s. Let me stop myself there and recount what I've just done. 1, 2, 3, 4, 5, 6 so far to where I'm at my very last carbon, and he gets a CH3 at the end. Okay, so this is our intro to organic chemistry or organic structures, compounds that contain carbons, and these hydrocarbons. They're all bonded together with covalent bonds, and they're so important for life and for a lot of the other fun things that we've got going on here. Carbon is amazing. It's my favorite element on the periodic table, and now you know why. Thank you, carbon.